So, I think we should be good to go now. So, I want to finish up the guidance for Lab 1. Execution control is the next little subsection. So we just got done going through this example where I called it dissecting a C program. So we went through this sort of simple C program and talked about each of the different aspects of it, and like where you include the libraries, where you declare function prototypes, defining external or global variables, or using this pound define syntax as well. We talked about that. Defining functions, so we talked about always having a main. Every C program, that's where the program starts. Talked about static types of variables so that it doesn't change in between calls to the function, which is really freaky at first, but once you get used to it, it's not so bad. We talked about C standard library, the symbolic constants using the pound define, automatic variables versus static variables, for loops, and how you go through them using the initialize statement and then the condition. It gets called at the top of every time through the loop to see if it's should continue, and the increments of your index. We talked about if, else, which is pretty standard stuff that is just like recognizing the syntax is all you need. And that's the main. And then return, a little bit about that. So now we're on execution control. So now I'm just going to walk through some of the key aspects that I think you guys probably have seen quite a bit of at this point, because you've been writing C programs now in the lab. So should be familiar. So, as we saw in the example above, C has the usual execution control statements, which include while, for, if, else, and else if. So these they work the same as in other languages. Everybody's familiar with at least one language if they're in this class. So nothing surprising there. Just need to learn the syntax for it. So just recognize that we're going to probably need most of those for your lab this week. So usually, so for and while are so close. They're the definition. I mean, you could use either one in most instances. So you might end up using a while loop if you want. You could use a for loop instead, or vice versa. Sometimes a while is the one that you need. Sometimes you can get away with a for. So the key difference, of course, is that for, you have to know how many times you're going to go through the loop before you start it, whereas while is not so with while. C data types. So C has only a few core data types. So chars, so they're single byte characters. Ints are integers, size of which is machine dependent. For us, an int is a 4-byte type of data, 32-bit. Floats are single precision floating point numbers, size of which is also machine dependent. So for us, a float is 32-bit as well. And then doubles are used more often if you're going to do a floating point number, because it uses twice as many bits to represent the number. So typically, a lot of times people will just say a float in 32-bit and double 64-bit because that's the most common instantiation. But technically, it could be different on a different instantiation of C. So it's good to not assume that that's going to be the case. There are also qualifiers such as short and long, which compilers typically take to mean fewer bytes for the specified representation or greater, respectively. So, like if you have a short int, I think for us that's a 2-byte piece of data, whereas a long int, I don't think we have, I'm not sure if there is a long int. I think that long int might just be the same as int for us, but these are things that you'd have to look into you'd have to unpack under the covers of the processor if you want to understand that. I actually can't remember off the top of my head. So arrays are just lists of values. So especially if you're familiar with MATLAB, arrays are sort of the foundation of a lot of how MATLAB works. Arrays are not as abstract in C. They're just really consecutive items in memory. So they're just lists of values. So they can contain any data type. So each memory address or each piece of data would fit in consecutive bytes in memory for an array. When declaring an array, one specifies the data type of each element and the number of elements, as in this. So if you have an array that you want to call X that has 10 doubles in it, this would be your declaration. Double X and then the square brackets 10, which tells the compiler to pre-allocate 10 slots. A double is going to take up 64 bits, or how many bytes? 8 bytes, right? So it's going to take up 8 bytes. So it needs to have 80 bytes pre-allocated for this 10 double array. So it does that when you declare this. Even if you don't, like as in this, if this is just a declaration and not a definition, then you aren't saying what the elements are yet. You're just saying that there are going to be some elements. So
this string, is it when we assign to the array? Like one character or?
So a string, for a string, it is an array. And we're talking more about strings, but a string is an array where each piece of data in the array is a character. So, yeah, so it's a char type char. Yeah. Yeah. So if you and we'll talk about strings a little bit more too. So excellent. Accessing element n of an array is done with the syntax x of n, which is kind of familiar MATLAB-y syntax, right? If you want the nth element, just x of n. It is important to note that the first index of an array is 0 in C. So it's 0 indexed is the sort of shorthand way of saying that. If you want the first element, you have to say, I want x of 0. And that means that this array, the last piece of data in this array is going to be at x of 9, right? There are 10 elements. The first one's indexed with 0, so the last one's indexed with the number of elements minus 1. So, great. Pointers. You guys have been getting to know pointers, right? It's a key concept in C. Pointer is a variable that is assigned not a value, but a memory address. So to get some variable x's value, x's value address, one uses the address operator, the ampersand, okay? So it's the and symbol, right? So ampersand. Like ampersand x. So if x is some variable that has a value in it, like maybe it's a double or something like that.
Can be an array?
It could be an array. It could be an array. X could be an array. It could be any data type, really. If it's any variable that's defined, it's going to have an address associated with it. And so if you want to know that address, you prepend this symbol to the variable name, and it returns the address. So it's like the yellow pages or something. I don't know. It's like nothing is anything anymore. Everything is just Google now. So it's like Google isn't very descriptive. In order to assign this to a pointer variable, the variable must be declared as a pointer to a specific data type. For x, an integer, a pointer to it can be declared with int, and then use the asterisk p. So if you're going to call the pointer p, then you need to declare it like this. If it's a pointer to a piece of data that has an int in it, you need to have int out front, or whatever type of data you're pointing to needs to be declared that way. This asterisk is, or star, we'll often just say star instead of asterisk, but it's the shift 8 on a typical keyboard. It's just a good old-fashioned asterisk. And if we want to actually make the assignment to p, then we would say, okay, take x, which is an integer variable, give me the address to it, and I'll assign that to p, which is a pointer to that address. Okay? I feel like at first this feels kind of weird, but then it starts to feel more natural after a while. To access the value to which a pointer p points, the dereferencing operator asterisk can be used, as in asterisk p. So when you declare it to be a pointer, you use the asterisk, which is kind of like suggestive of this notation here. So you use this asterisk if you want to know what the value is. So for instance, if p is pointing at the address, pointing at x, then if you want to know what x is without actually saying give me x, you'd use the dereferencing on p to have it show you the value. Okay? So let's do an example. I think the example makes it kind of more clear. So simple example. And this is all, executable C code. So if you want to like copy and paste this in and just play with it, I encourage you to do that. So declare, well, actually, so we just have a main, just include the standard input-output header file, so we can use the printf function. That's why we pull it into almost every C program, because we want to use printf a lot. So we do that. We declare static int x, its initial value to be 1, okay? And then we declare, so when you do this, you can declare in the first half of this and then assign it a default value, and this like right afterwards, instead of having to then have a new line that says x equals 1, you can declare it and assign it at the same time. You'll see this a lot, so I use this because if you read somebody else's C code, you're going to see this all the time. It's just easier than writing 2 lines. And they even have competitions, I'm not kidding you, for writing the most obscure C program. You try to make it look as obscure as possible, like doing something so that people can't even figure out what your program's doing. It's really easy to make it hard to figure out what people are doing. So I try not to write my code like that, but obscurity does creep in sometimes, especially when you want to compactify it, which is always something that everybody wants to do, is compactify it, and then they end up in making it unreadable. So assign 1 to the variable x, and then we want to also assign a pointer to the address that x is at. So we get x's address, and then we assign that to a pointer p. So that's how to do that in sort of one step. We had to use int here because we had to match the data type that it's referencing. And then I'm just going to print 4 things. Okay. The first thing, I'm just going to print x, which we assigned 1 to x. So thank God, it comes out 1. The world makes sense. That's good. Okay. The second thing we do is I say, okay, what's the address that x is at? And I print it out. So I'm printing using printf. Notice that, so this is just the new line character, which makes it so that it prints the next thing on the next line, right? But I'm also using this format string %d. Look up the printf documentation, and you're going to find, and I'm sure you guys already have done this for your lab, but you're going to find that %d is something that will print out numeric types for you. Now, if you want to print out a pointer to an address, you can't use %d, you have to use %p to do that, which will print a pointer. So that's what we're doing with this address operator, x. So what's the address of variable x? And we're going to print that pointer. And it gives us this thing. Now, this number starts 0x, which is kind of weird at first to look at. But this is just C telling you this is a hexadecimal number. Okay? So whenever you have 0x, it's hexadecimal. And when it returns an address to you, it's always in hexadecimal. Now you could cast it to another type, but as we know, a hexadecimal number could represent just any number, and it does. So an address in memory is just an integer. So we could convert this by casting it to an int, and we'll do that later on. But for now, we'll just look at the memory address in hex. And then we look at the pointer, p, that we assigned. And we expect it to be, we assigned to p the address of x, which we just printed out. So we expect it to be the same thing, and it is.
P and x have the same address.
So p points to x's address because we said that p is a pointer that is pointing at x's address. So if you look at x's address or you look at p, they should return the same thing. And they do. They return the same thing. Now, if you want to dereference the pointer, which is to say, if you want to look at the contents of the place in memory that the pointer is pointing, which is, in this case, p is pointing at the variable x, and it has value of 1. So if we use the dereferencing operator here, star p, we should get back the value of the x variable, which is 1.
So if it is the string which contains a lot of character, show up all the character inside the last.
So it actually pointers to an array or pointers to a string point to the first address. So on the side here, a string is going to be, say, a 2-byte character, and then another 2-byte character, and then another 2-byte character. So say there's 3. Say this is like, yeah, what's a good, I know. Most of Dane's name. Okay. Dan. My good friend Dan just moved away. Well, actually, he's on a flight today to Thailand, and it's really sad. So we're going to use his name in this. So Dan would be actually six different bytes in memory, a string together. So if you assigned this string to the variable x, then x would actually just be a pointer to the first address, which is this byte right here. So you would have all of these below it, and you would be able to access them. And you know when you reach the end, because the very last one, as we'll talk about, is the null character. And so you can keep reading a string until you reach the null character, and then you know you're done with the string.
So when we print the pointer p, in this case, if x equal to Dan, what it will print out on the console?
It would print out D. Oh well, it would print out the ASCII, depending on how we did it. We could have it interpret it to ASCII, but the piece, it would return this piece of data, essentially, the D piece of data. If x is an array and you just ask for x, it returns the first piece of data from the array. It doesn't return the whole array. It just returns the first piece of data.
Can you return a specific number in that array? So
It can.
X of 6.
Well, what you would do is it would be like the second. If you wanted the A, you would do x of 1 would give you the A character code. X of 2 would give you N, etc. So it works just like another array, but the pieces of data in it are characters instead of integers or floats or something. Okay.
Another question.
Yeah.
In the code, so it says like the dereference pointer equals, so in the third line or fourth line?
Yeah.
So star p equals ampersand x. So isn't that saying like the value of p equals the address of x?
Exactly.
But then why does it print out 1?
It's because of
Because you dereference it. So if you print out P, it prints out the address right here. But if you print out, so if you hit it with this, so the dereferencing operator is like it's not being used as so the star isn't really being used as dereferencing in this declaration. This declaration is really saying that P is a pointer. And in fact, so what we could have written is static int star P semicolon, and then said P equals. So P equals ampersand, so address of X. So that's why it's a little weird. It looks a little weird when you declare it and assign it in the same line. And I'm glad you pointed that out. But when you use it later, P has the value in memory. P is, just another piece of data in memory. But its value is just an address to some other piece of memory. So if you evaluate P, it's going to just give, if you print P, it's just going to print the address. If you use the dereferencing operator on it, if you star P, it'll give you the value at that memory address. Okay. And I encourage you to play with this. So if you've got it on your laptop or you're in the lab, whatever, you can just run these programs and print stuff to the console, right? You can just run these. Another thing, and when I've got time, I'll probably try to put together a little tutorial on how to do it. It's pretty straightforward, though. If you've ever used Jupyter notebooks before, you can get and that's what I create this in. It's like a Mathematica notebook where you have all these cells and you can evaluate them. But you can put a whole C program in there and evaluate it, and it'll print out the stuff from the console. And you can just play around with it, tweak it, and kind of. I feel like when you're learning a new language, you have to have a playground to play it in, right? And I kind of did a little. There's one of the resource sections is a description of how to do just install the GCC compiler on your machine and just compile C programs and run them. So there's that too. So there are different ways to do it. I encourage you to find some way to play around with C, because the lab environment is okay, but it's pretty specific, and you have to compile it and then deploy it to the machine to run it. But you can run C on anything. So it's not everything is identical in all the instantiations, but if you use GCC compiler, you probably won't run into very much that's different. So keep in mind that there might be a few things, for instance, the number of bytes that a certain data type takes up on one machine might not be exactly the same as another machine, but most PCs is going to be 32 and 64, and so yeah, it's not like it's a huge difference. You could still do a lot of C playing around without getting yourself into trouble. So yeah. Anyway, and it's kind of fun too. I bet that you guys haven't had a lot of experience writing source code, compiling it to an executable, and then running that executable. It's pretty cool. I mean, that's the source code for commercial software is not released. They've released the compiled versions. That's why when somebody you run MATLAB or something, all the source isn't in there. So it's not like somebody can just copy everything out of MATLAB and just throw it around. Those are compiled functions that are not visible. The source is not visible in them. So yeah, so it's kind of cool to do. So this program would run on anything in C, and it would print to the console these things, and it's kind of satisfying. I recommend trying it. Okay, good. An array variable, say an integer array of length 10, just for instance, declared by int z10, is just a pointer to the first value in the array. So this we talked about a couple minutes ago. An array name is a constant pointer, which is a special type, so it cannot be reassigned. So for example, if PA is an array, you can't say PB equals PA. It's a static pointer. It's a constant pointer, and so you can't do that assignment. And a compiler will complain. So
You assign once and then you use it.
then you use that one. Yeah, you can't essentially create an alias for it. You have to use that variable. Yeah.
Because the memory is recording this PA already, and it will not accept another one that equal to PA.
Exactly.
Same address.
Right. And this is not true of every pointer, but it is true of pointers to arrays. So, okay. Cast operator. This is another one that you guys have probably encountered a bit. A cast operator on an expression to type, and I'm just going to use this italics as a sort of expression here. So type. So this could be, int, could be car, could be double, the usual suspects. Is you put parentheses around the type that you want to come out, and then you give it the expression. This expression is going to evaluate to some type, right? So this thing could evaluate to an integer. It could evaluate to a double. It could evaluate to an int. It could evaluate to a whatever character. And whatever comes out of it, we're going to convert to whatever type we put in the parentheses. Okay? So there are rules that each instantiation of C will have for this. And they usually make sense. Sometimes you don't know what's going to happen when you do it, because it doesn't make a ton of sense. Like, especially when you do from like a character representation to a like double. Like, I don't know. What's going to come out of that? Maybe nothing useful. Probably nothing useful. But oftentimes you're doing something like a really common one is that you need an integer type and you have a floating point. And so you want to take the floating point and you want to turn it into an integer. That would be a common thing. So for instance, like maybe some function only like accepts an integer for this argument. Maybe the floating point is like 4.72222 and you need it to be, you want it to be an integer. So if you cast it to an int, it does something. It isn't always what you want exactly, and so we'll talk about this. But it will try to make this into an integer. It's something that makes sense. It's not going to give you like 7,000 back, but yeah, so we'll talk about that. So it does not affect any definitions in the original expression. So you know how, like, one of the things about C that kind of freaks people out at first when they haven't seen a language like this is that, especially when you get into like increments and stuff like that, is that you can have inside of an expression something that assigns, that changes the variable that you have in there. It can even be on the right-hand side of the equals sign, right? It doesn't even have to be on the left-hand side of the equals sign. And you're actually doing an assignment in an expression, which is not, MATLAB does not like that. I've never seen at least anything in MATLAB like that. So if you're familiar with MATLAB, this is not going to help you in this case. But inside this expression, you could have something going on there. But this casting thing doesn't change anything there. So if, say you had like the variable x here, and the type was int that you were casting to, and this is like a float or something. So this would do casting, but it doesn't change the definition of x. Okay, it returns an int from this statement, and you would have to assign it to some new variable like y or something like that. But it doesn't change the definition of x. So that's an important thing to remember about it. And there are some statements that will change the definition of a variable inside of it, and others that won't. And understanding when something's changing the definition and when it's not is something that you just have to know. So you have to know this about the language. So it represents the expression and the new type in accordance with certain rules. It doesn't affect any of the definitions in the original expression. Rather, it returns a new expression. Suppose you have the following. So declare a static integer a. I'm trying to think if int is 2 byte in our instantiation. I was thinking it was 4 byte. I'll have to review that. But let's say it's 2 byte. It's short, I think, is 2 byte. But anyways, let's say int for a second is 2 byte. And that a long int is 4 byte. Okay? They're both integers, but represented by a different number of bytes. So there are more integers that you can represent in this one than in this one, right? So if you do a casting from B into A, you could run into trouble if you can't represent the integer that was in B, right? So if we go down here, say B is equal to 3, well, we could easily cast 3. I'm confident that in the int representation, we can represent the integer 3, no problem. So this casting should be no big deal. We took a long int to an int, no big deal. But there is a potential when you do this for there to be truncation. If you went the other way, if you went from an int to a long int, you wouldn't expect there to be any truncation because you're going to a larger number of bytes to represent something. But since we're going to a smaller number of bytes, you have to be careful that you know that you're not going to be truncating, or if there is truncation, that it's not a big deal. So recognize that that is happening. When casting to an int from a float or double, beware that truncation does not round in the usual sense. It simply drops the fractional part. It is preferable to use the function round provided by the standard header file math.h. So it's the standard C library header file math.h. So if you cast 4.2 to an int, well, it's pretty easy to. So that's say it's a float or a double, and you cast it to an int, it's 4. But if you cast 4.7 to an int, you would hope it would return 5, but you'd be wrong. It still returns 4. And that's because it just completely just ignores the fractional part. So that's why you should use round if you're worried about that happening. Depending on the application, you may or may not want to round it, but often when we do that, when we're looking for an integer from a float, we're looking for a rounding of the float. We want the closest integer. And if you want the closest integer, casting is not for you. Run it through round instead.
So I saw in our first level, we type the data in.
Mm-hmm.
When we return the value to the main function, it's not equal to what we are typing in, like 12.85, and then we just turn from 84, a lot of number behind in this debugging panel. So this is how the machine runs, that the value will not be as equal as this.
I don't know about that specific instance, but that this is one potential source of that. There are certain situations when you don't even explicitly tell C to cast a variable, and it will cast a variable. So, for instance, if you declare in your it's fine. Let's go back to the example for a second. If you declare in your function and in your prototype here that the argument is an integer, then whenever you put something into sum that's not an integer, it'll cast it. So you don't even necessarily have to notice it. You could just use sum, and it's assuming that you know that if you give it something that's not an integer, it's going to cast it to an integer. So you could be thinking, oh, it's going to expect, sum's going to expect a float, but it's not, and it casts your integer, and you end up getting weird numbers. This is one potential source of that. Yeah. So casting, you can explicitly tell it to cast, but one of the rules of C is that if you expressly declare that an argument to a function should be of a certain type, which you technically don't have to do, but is strongly encouraged, and we adopt as something that we do in class, then it will cast if you don't provide the right one. Okay, so find where we were. This is exactly why ebooks kind of suck. Okay. All right. Incrementing and decrementing. Yet another thing you guys have been wrestling with. Okay. So, for an integer x that is equal to 0, instead of writing x equals x plus 1 to increment x by 1. So you could say x is equal to x, which was 0. And now we want to assign 1 to it. We want to add 1 to it. So we'll say, give me the old x, add 1 to it, assign that to x. So it'll overwrite x, which is a common sort of thing that you've done before in MATLAB and whatever, right? That's a common thing to do. But we can write, because we have to do this a lot. We have to increment by 1 a lot, especially in like loops. This happens all the time. So you can either write plus plus x or x plus plus. Okay, both of them will increment x by 1. The former is called a prefix operator, and the latter postfix, both of which increment x, but they are interpreted differently in the expression. So plus plus x increments x, then uses it in the expression in which it appears. So this example, I think, explains that pretty well. If you have the statement n equals plus plus x, it's a prefix plus plus, so it assigns 1 to x, okay? So it was 0, assigns 1 to x, then 1 to n. So it does the plus plus before it uses it in the expression, okay? X plus plus uses x in the expression in which it appears, then increments it. So x plus plus would say, okay, x is 0 coming in. We'll use it with x equals 0. And then n will equal 0. And then we'll increment it so that x is then equal to 1. So notice that this statement assigns a value to x and it assigns a value to n, which, once again, an expression that doesn't have an equal sign can you could just say at one entire line in C could be plus plus x, semicolon, and you never said x equals anything, but you did change x through an expression. You can use that. Oh man, I gotta go get my charger. You can use that in an expression. God, my battery is just like starting to really suck. Just got past my Apple Care protection, so now is the time. Okay. So the decrement operator, minus minus, also has prefix and postfix versions, but subtracts 1 instead of adding. The next example shows how pointers, not just ints, can be incremented. They can also be decremented. Incrementing a pointer moves it not to the next address in memory, but to the next piece of data in memory, skipping the necessary number of bytes. So it's actually kind of smart. So he says, we know that you don't want just like half of a character or part of an integer, 1 byte of memory. We know that you actually want the next piece of data. So it actually knows to go to the next piece of data when you increment an address. Okay. Operator precedence and associativity. So take a look at resource C3. There's a table of operator precedence and associativity. And it also has a description of what that means exactly. But precedence and associativity, focusing on precedence here, it's like when we write 7 times 3 plus 6 divided by 2 minus 1, we know that you have to do the 7 times 3 first and the 6 divided by 2, and then you do the additions and subtractions, right? We have that built into our our understanding of our operators, you know, plus, minus, divide. And you guys spent a lot of time, what is it, like, I don't know, there's acronyms. And then parentheses are always the ones that have the highest priority, right? You can always put parentheses around things if you're not sure. Okay. So, these are true of all the operators in C as well. They have the same things. Most of them, I mean, the ones that we're familiar with, like plus or whatever, they tend to have the same relative precedence, but then there are things that are not clear, like what has precedence. So what I did is I went ahead and just like printed out a bunch of different cases of just like mixing these three operators together and then just like trying to parse it. So I just went through and I redefined x and p to be x is equal to 5 and p is a pointer to the address of x before I did each statement and printed it. Because some of these statements will change p and x, right? So I redefined it every time and I printed it just to see what it did. And I also printed what I was doing at each step so you could see. So I'm going to let you guys ponder this for a moment while I run and get my charger. And when I come back, I want you guys to explain all these lines to me. Okay? I'll be right back. It'll be like 30 seconds.
This one? Yeah. Kinda. I mean, not that one, but so B only. That's the pointer to the address. Number of days. Abstract B. That's to the value of days. Yeah. So we have an array that has like 6 numbers, and we chose abstract B. We chose automatic. The first number of the value of x.
Yeah.
Yeah.
Yeah. Because you had B chosen the
Unless I specify with a specific number.
So unless you put like X parentheses like
3, let's
6,
say.
then
Yeah.
it's 6.
Yeah, it's Now true. we're coming
It's
with
like,
the
it's like a MATLAB with an
Yeah.
array when you want to like get like third number to be
Yeah,
like big and parentheses 3. Yeah.
Alright.
that point.
Yeah. No, this makes sense.
Okay.
It's nice having you read it to us instead of like reading it and then looking back at like trying to document it, forgetting what I just read, and being like, what does this mean?
Yeah. I think this method seems to, I don't know. I'm still playing with different stuff. As you can tell, like I'm constantly revising how I do things. I can hardly stick with anything long enough to try it, and then I gotta fix it and make it better.
So it's nice working on it first though. Being kind of just lost.
Yeah.
And then being like, okay, so that's it.
So let's take a look. These first 2 lines give me exactly the same thing. So I take P, which remember is a pointer to X, and I cast it to an int. That's the first statement, and it returns this. So what am I looking at? What is that thing?
That's the address.
That's the address. It usually returns it as hex, but I casted it to an int, so it converted it for me, and now it's just a base 10 integer.
So no more OX before.
No, yeah, exactly. So it doesn't start with 0x and then the number. Okay.
Because it is an integer.
So then the next statement I once again I cast to an int. I have p. I do p plus plus. So it returns exactly the same thing. Why did it return the same thing?
Because it increments P after it prints out.
Yeah. it used P, did the casting, and then it incremented P. So it's going to give me the same thing back because I'm not printing out P, I'm printing out this expression's return. Okay, the next one, same thing except for I do the plus plus before, prefix operation.
Add first.
But notice it incremented, it didn't just go 1. Why did it move 4?
Because that's the next memory location where it has some data.
Yeah, it's a new piece of data because the int, at least on my laptop, which is where I ran this thing, with GCC, an int is 4 bytes. So it had to go 4, had to add 4 to get to the next one. So that was kind of fun. That was, I think, why in my mind. But I think I'm pretty sure on our machine, I don't know. I wrote 2, but I think I might have been wrong about 2 bytes representing an int. Okay, so very good. We've got the next 3 all return 6. Okay, so let's look at this. I've got P, our pointer. I've got the dereferencing operator, and then I've got a plus plus, a pre-plus plus. So
You take the value of x and plus 1 and
that's right. The value that the P is pointing to, which is the value of x,
then plus
and then plus plus, we do that before we return the expression. So it's going to add 1 to 5. X was 5, so we add 1, we get 6. And this thing, it turns out, no matter how you group it using our parentheses, we end up with the same expression. So you can have explicitly P being dereferenced, and then plus plus. You could have explicitly the pointer coming in. The dereferencing operator will still work on it if it's inside parentheses. That's just fine. Now we flip it around. We put the plus plus on the other side, and we get dereference P plus plus afterwards. So notice that one thing that, here you could say, well, it could do P plus plus. P plus plus would just be moving to the next memory spot in memory, right? First. And then give in dereferencing. It's not what it's doing. It's doing the dereferencing first because it gets the value of 5. The post fix plus plus happens, but it doesn't happen until after this expression is evaluated to 5. It's a little bit more obvious in this case that you're going to dereference first because you've said explicitly, give me the dereferenced P, and then after do a postfix plus plus, so returns 5, and then it's the same if you do parentheses around P. And then we get weird. And then we say increment P, use it, so increment it first, and then give me, then dereference it. So we're incrementing the pointer
to a different address and then it
to a new address in memory, and then we're returning what's there. Then it turned out it's 0.
There's nothing inside the
It could have been, I don't know, I mean, it just was whatever was there. 0 was there. So
Why 0? Just not null.
that was, to my knowledge, completely random. I actually don't know for sure why it came out to be 0.
Because
I think that,
the next address, there is no data in it, so it should be null.
yeah, but if you had written, I actually don't know this. This is a little bit of a nuance, I don't know. I'm not sure if you had something in that memory address from before the program started running, if it would read that piece of data from it. or if anything that you haven't used in the program would come back as 0. But if it was in the program and you went to the next address and it was something that was in there, it wouldn't have to be 0. It could be anything. So if you were, for instance, referencing if P was a pointer to an array, you would take the second value from the array, would be what you would get there. Yeah.
Could you more explain line 10, please?
Yeah. So what this is going to do is, it's actually the same as line 11, so it's a little bit more clear in line 11. It's going to, this increment operator is going to increment the pointer, which means that in memory, it's going to find the address in memory, you know, whatever it is that it's pointing to, and it's going to move it to the next address where there's another piece of data. So it's going to move, so if you've got like a 4-byte piece of data there, it's going to move down to, it's going to move down 4 to the next piece of data, and that's where it's going to point now. And then you dereference it, so it's going to actually give you whatever is there, which is 0. In this case, that's 0. If this was an array, if it was a string, for instance, then it would be the next character.
This thing is interesting because how when we put the DVD, then it is the read and write DVD inside the computer. How does it know that it is blank or it has something written on it?
In the case of DVD, I don't know. There's lasers involved. They bounce off. No, yeah, I'm not sure how it decides that. I'm guessing that when you write, there's some like first few bytes that tell you what the contents are or whatever. And if it's never been written, it probably looks a certain way. I don't think it probably scans the whole disk, be my guess.
So could you assign like a value for, like if you did star plus plus p equals 5, would then that come out as 5?
I don't know for sure. I don't want to say because I don't know. And actually, this came out of these specific combinations came out of a Stack Overflow question that I was looking at, because people were having a discussion on there of what would happen if you did these different things and why. And they were like, and I wasn't actually very satisfied with what people were saying, and nobody did it. And some of the explanations were wrong on there because when I actually tried it, they came out wrong. So I posted this as an answer and said, I don't know, this is what it does. So try this. But so I think when you get into that kind of thing, it's that's a little subtle. Can you write to that incremented pointer, dereferenced pointer? I believe you can, but I actually don't know for sure that you can. So, because you're not declaring a variable.
Yeah.
And I'm not sure if it'll let you write if you don't declare a variable for it. It's an interesting question, though. I like the way you're thinking about it, but I hope you find out and tell me, because I'm interested. If I had maybe after I end this lecture, I'll queue up my C compiler and we'll try it. We'll see if we can assign something to it.
So So we cannot assign the address, I mean the pointer to any specific value that we want.
So the question I think he's asking is, say you increment your pointer, can you use that pointer to that incremented address that you sort of wandered off into? Can you assign something to it? I don't know exactly the answer, but we'll find out. I think we'll queue it up after this. We'll just find out. So I think that's the best way to answer this question. So the next thing we've actually talked about quite a bit, strings are arrays of characters terminated by a null, which is a pointer that casts to 0. So if you cast it to an int, it will cast to 0. For instance, the string hello could be represented in memory with corresponding ASCII codes as follows. So you'd need the ASCII code for H, ASCII code for E, ASCII code for L, L, O, and then you would have a null character. So that is, I mean, we've kind of been talking about that as we went. Because everybody, as soon as we started talking about arrays, was interested to know about character arrays because, well, you're using them in lab. So, okay, function argument passing. So all function arguments in C are passed by value. That is, the function receives its arguments through temporary local variables called automatic variables, which we talked about a little bit in the dissection of the C program in the earlier section. When it's necessary to pass back an argument with a changed value, the caller can provide the function with the argument address via a pointer, and the function must access the variable through the pointer. So if you give the function a variable x, it's going to define a new variable like x2 inside of that function. Just like in MATLAB when you have a function, it doesn't have any access to the variables from the function that called it, right? It can't write to them, it can't read them. Unless you declare a global variable, which is something you can do. Or in C, there's this other thing where you can give it the point, if you give it a pointer, that address in memory is a valid place if you're inside the function or outside the function. So that's one way to get around this automatic variables aspect. Although one of the reasons why functions have their own scope, their own namespace, is that it's nice to feel confident that you're not in another function's namespace when you're down in. It sort of limits the amount of things you have to keep track of. So although it is nice to like pass a pointer and use that address in memory, sometimes it's nice also to just keep the namespace clear. So there's a reason why not every variable is a global variable. So it's nice to know when you know how to circumvent this, but it isn't something you want to always circumvent either. So, all right, a potential alternative is a global variable, which is defined by extern. Okay. Literal of a long, this is like just a little note. So for the compiler to recognize a literal number as a long, so a literal number is one that you just type out, like using your keyboard, like 723. That's a literal. If you want the compiler to recognize a literal that you write out as a long, it must have an L suffix. For instance, if val is a variable that's a long, and you want to compare it to the number 32767 in an if statement, for instance, then you want to compare apples and apples, right? So you want this thing to also be a long. And if you write out the literal 32767, that is by default in the compiler going to be interpreted as an int, not a long int. So if you want it to be a long int, then you have to write out the L at the end. So the L is the key there at the end. Just like 0x means that's a literal for a hexadecimal number. L is for a long.
What the difference between the long integer and integer?
It's more bytes. It has more. You can represent more integers in a long int than an int. And I'm really regretting not looking up which number of bytes is used for long and used for regular int and used for short int before this lecture, for our case. But it's usually like 2 and 4 and 6 are like possible. 2 and 4 and 8 bytes are common for long versus int versus short.
So is it okay to like assign like variable capital L?
That's a good question. So I don't think there's any problem with capital L. I think that the only time that is interpreted to be long is when it comes after numbers in a literal like that. So I don't think there's any issue with that. If you wrote down this and L had already been defined to be something, that wouldn't give you any issues. If you had like a multiplication in between there, then it would. But there's no ambiguity if you don't have that. Because in some languages, like in Mathematica, if you have a number and then a letter, it automatically interprets that as multiplication. C does not. So it would not think, oh, this is multiplication. So, and then, yeah, so this if statement is one such case. Where it's one case where you would write a literal down and you would want it to just interpret it on the fly. The same would hold for hex representation of something. Null detection. So I did this just because there was some questions about detecting null in the program. So I just did this, and I sent this out already, so you guys have seen this. But the following program gives some insight in detecting a returned null character. So what I do is I first just print out null, which is a pointer, and then I print out a null that I cast to an int. And then I also try to detect null using 3 different things to compare null to. So say that the expression on the left evaluates to null. I want to see if I just do the double equals, which is a question of equality between 2 sides of an expression in C. I want to see if these will work. And the answer is, if you look at the next page, which is way over here. It works. So first off, the pointer points to 0, which the null always points to 0. And if you cast it to an int, it gives 0. So that's like the null is a pointer, specific address 0, and if you cast it, it gives you 0. So all 3 of these ways work. So I'll go back to the 3 ways that we check. So the 3 ways we can check, or these are 3 that I came up with on the top of my head. I mean, you could come up with other ways to check too, of course. But I say, is null equal to 0? And if so, print. And it did print. So it worked. If null is equal to 0x0, so just a literal, that's a hex version of 0, that also works. And can you just type out capital NULL, null? Does that return an equality with null? It does. So you can use any of those 3 to compare to a character. I think there was more confusion in the case of the lab about if the function was returning null versus writing null to the string variable. That was, I think, where the confusion was coming in. Not as much comparing it to what to compare it to, but anyways, for whatever it's worth, these are 3 ways you can check to see if a character is null.
So can you dereference null and have that equal 0?
Another question I don't know the answer to. The address is 0. When we do a little C compiling after this, we'll check. Let's see if we can dereference it. I don't know if you can dereference null. It's a good question. You're just trying to break it, Dane. Stop trying to break it.
Put it somewhere, not to this 0x0 anymore, 0x1. For example.
Yeah.
you want to move it
Increment the null pointer. Oh God. So I'm not saying that this is not good to do.
Yeah.
I'm just saying that you're asking for trouble.
So
So-
he's trying to write the most obscure program.
That's right. I
Even
think that's what you are
cannot
doing.
check the correctness to correct the code anymore.
So, okay. So there's the last thing I wanted to mention. This helps with the assignment and not with the lab, but since they're coming at the same time, I'll do this too. So, signed hex numbers. We did signed binary, and of course we know signed decimal numbers, but we've not done signed hex. So I wanted to, because in the homework, I think there's one where you have signed hex numbers. So in addition to specifically C-related topics, above the following is useful for the first assignment. So we can change the sign of a signed binary by taking the 2's complement, right? So analogously, to put a negative hexadecimal number into a signed hexadecimal form, take the 16's complement. So we took the 2's complement when we wanted to take to find the negative representation of a positive binary number. But in order to do it for a hex number, we typically use the 16's complement representation. So the steps are take the 15's complement and then add 1. So you might remember that when we did the 2's complement of a binary number, we took the 1's complement, which is actually just flipping all the bits. That's one of the ways we learned how to do it. Flip all the bits and then add 1. That was one of the 3 ways we learned how to do the 2's complement. So the 15's complement is not exactly flipping all the bits because we have 16 possible ways of 16 possible values for each numeral. So we're gonna do an example. So I'll essentially show you how to do this by example. So I'm going to convert 3a into negative 3a using the 16's complement, using the 15's complement, and then adding 1. That's what I'm going to do. So the way that I think is easiest to do this is to just write a nice little table. So what you do is you write in descending order on the left-hand column the characters that you have. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh wait, I think I went one too far. Too far. That was bad. Too far. Okay. And then what we're going to do, so we got half, we essentially go down until we get through half of our characters, and then we're going to fold it back up. So 7, so it was obvious. There are 8 characters here, and we're going to fold it and write the rest of our 8 back up the other side. So 7, 8, 9, and then we'll do A, B, C, D, E, F. Okay? And then we'll use this table to take the 15's complement. Now, before we do that, so I'll say 15 complement. So let's write 3a down, but we're gonna at least represent this as a nibble. So 0, 0, 3a, and we're gonna convert each of these numerals, so one at a time. So what we do is we just look up in the table what's next to each of these numerals. So 0 becomes f, 0 becomes f, 3
Become C.
becomes c, and
5.
a becomes 5. Okay, so that is the 15's complement. And then we need to add 1, which is really rather easy. Even in hex, adding 1 isn't so tough. F, F, C, instead of 5, we now have 6. So this is our negative 3a representation.
So why was it 4 digits again?
So we could have gone more, but we typically, anytime we have hex or anytime we have hex or anything else, we can pad with as many zeros as we want. So in case there's overflow, we tend to like give it a little bit of room. As long as you're okay with just adding another one, like we are in decimal, we're comfortable not padding with zeros. But as long as we remain comfortable padding, if we need to the left, doing overflows, we're fine. And actually, I was mistaken calling this a nibble because, of course, memory can only hold a lot less information in hex than it can in binary. In binary, 4 is a nibble, but that's specific to binary. So I shouldn't have called that a nibble. So if we had kept going, this would be 0, 0. This would be F, F, and there would be F, F out here, just forever. So we could go as far as we want. As long as we get, so if this is a 4 numeral representation of 16's complement, but if you wanted to go to an 8 numeral representation, then you would have to have 8 numerals here. So
I'm kind of confused because, when you add zeros out in front of 3a, it doesn't change the number. But when you're adding f's out in front, it's changing the number.
yeah, so you do, when you do the complement, you do have to choose, you'd have to choose the number of, so if it's in binary, you have to choose the number of bits you're going to use to have as the complement. So, yeah. I guess we should say that this is true. You can go out as far as you want. But when you do a complement, you have to have a, what would you call it? I guess a convention for how many you're going to use. So if you're going to use a 4, I always want to say digit, but that's really just for base 10. But a 4 numeral representation, like when we did 2's complement, negative number representations in binary, I think we did 8-bit 2's complement. So the idea is that if you add 0, 0, 3a and f, f, c, 6 together, you should get an overflow every time a and 6, 0, c and 3, 0, carry, 0, and f, 0, carry, 0, and f with, with the carry, 0, and carry the 1. And essentially, if you keep writing f's here, you're going to keep carrying the 0, so you'd have to have, your 16's complement would have to keep going with the f's, and then your overflow would keep carrying. So, yeah, the 2's complement, or the 16's complement, all these f's out here are going to be important if you have a higher number of numeral representation, but not as important if you have so if you stick to a 4 numeral, you do that, and your overflow then is going to be like that. If you have a 5 numeral, the overflow wouldn't happen until the next one over. So in a 16's complement, if the first numeral is an f, that's a negative number. Whereas, remember, in 2's complement, if the first numeral is, the first bit, in this case, is a 1, then you have a negative number. So it's very analogous, but with more characters. Does that make sense?
Mm-hmm.
Yeah. And in the homework, it's essentially having you just switch representations a couple times and add them together. It's more important to have like an understanding of kind of how it works, and knowing why we do hex, why we do binary, why we do decimal, then becoming great at doing the arithmetic is fine, but I mean, that's like literally why we have computers. So actually, it was invented for people came up with a system for computers specifically. So we should be able to do it, but we don't have to be like maybe pros at doing it. We could be. I mean, just some people like to go to the movies. We might like to add hexadecimal numbers. Yeah. Any other questions?
Yeah, so and then adding the 1, do we just add to whatever number we have?
Yeah, so it's always the rightmost numeral. So the rightmost numeral is going to increase by 1. So if that rightmost numeral was an 8, then it would be a 9 here. If it was an A, it would be B over here. Yeah. What if this numeral was an F?
You just go back to 0.
It would go to 0, and you got to carry 1, right?
So the next one, if it is C, it will be D.
Exactly.
Okay.
So if that was F, then we would write 0, and then we would write, instead of C, it would be D, and then we don't have to carry anymore, so it'll be FF. It's the same old operations, with new characters, which is freaky, but
What
good
if
freaky.
The hexadecimal number are 5 terms, something like this, like 3AB, 34B, something like this.
Say come again.
It's more digit of the hexagonal number, like 5 digit of hexagonal number.
Oh, like if we just kept going instead of 4, we did 5.
The
or we
given,
did
the
6.
given number, we want to learn the range. Here, yeah.
So 3A.
Yeah.
Yeah, so we could totally do that. So if you wanted to convert 3A, but you wanted to do it in...
Not 3A, but the given number is long.
Oh, yeah, if it's bigger than that, then you have to go to a higher representation than just 4 numeral. You'd have to go to an 8 numeral or 16 numeral or, yeah.
12 can be 12. Everything
Yeah,
by
so, yeah, as long as, well, and in fact, with hex, you could even, if you're trying to think about it in terms of representing it in a computer, with hex, each numeral that you add is totally valid because you're adding 16 at a time, right? So, yeah. So you can just keep adding 1 hex at a time, and that's fine. You can still do the representation in a computer, which is fine. So, okay. I think we've pretty much got this, because I mean the class isn't really about different numeral system arithmetic things, but I do find that this is probably like one of the least familiar concepts is like adding in these things, so gotta kind of go through it. And so now I'll kind of talk about, just for just a moment, about where we're headed next. So this lab, we're almost done with it. We're going to have 2 more labs pretty much using the same stuff, but we're going to dig down to these lower layers. And in fact, it's right here. So for lab 1, by Friday, we'll have double in and printf LCD written, our own versions. And then in lab 2, we're going to write fgets keypad and getchar keypad, which we're using in this lab, in lab 1, but we're using the library function. So we're going to write our own versions of those as well. And then in the final lab in this series, we're going to do get key and put char LCD. So we're getting lower and lower level for the next few labs. And then we're going to kind of switch gears to another sort of segment in the course where we're going to do some sort of interfacing concepts, and we won't be writing. I mean, then we'll just keep using these. So we'll say, okay, these are good. We've got our LCD interface. We know how to, we can write things to the LCD screen. When people type in stuff in the keypad, it shows up on the LCD screen. That's all good. And then when we have a key stroke that's typed in, when we have a string of numbers, we can get that string and we can convert that to a decimal number, a double, and then we'll be able to use that in the following labs when we build. Then we're going to start interfacing with, there's an encoder, and then we'll start doing pulse width modulation, that type of thing. So there's a lot of stuff that we're going to sort of switch over to. So this is probably the most kind of, I guess, the furthest away from engineering programming that we're going to be doing. Then later on, it'll be more specifically like how do we implement, like how do we read what an encoder signal is sending to us? What do we do with that? How does that work exactly? And in the theory side, we have to look a little bit deeper at like the CPU how it takes instructions, registers, that type of thing. And then we'll start switching gears. We kind of try to stay parallel, but it's tough to like perfectly time the theory. But we're doing fine on our schedule so far. So, yeah. Any other questions? I'm finding that the guidance for the lab portion takes a lot more of the time than the theory portion than I was thinking. So it's fine, totally fine. When I was a TA for this course, I had my notes, and like mostly it was on the lab, and I was like, why is this all about the lab? I went back to my notes, and I realized now, it's mostly talking about the lab. So we'll walk over there. We've got some time, so.